Hello Math 3311 students. Let's begin lesson 4, prime number theory. I hope everybody remembers what a prime number is. An integer greater than 1 is called a prime if its only positive factors are 1 and itself. For example, 2 is a prime, 2 times 1, nothing more. 3 is a prime, 3 times 1 and nothing more. 5, 7, 11, 13, 17, 19, 23, those kind of numbers are called prime numbers. On the contrary, an integer greater than 1 that is not a prime is called a composite. For example, 9 is a composite number. 9 times 1, yeah, okay, we can do that. You can get a trivial pair like that. But also there is a non-trivial pair of factors, 3 times 3. How about 12, for example? There are many non-trivial pairs. 2 times 6, 3 times 4. Yeah, you can do 1 times 12, the trivial pair, but non-trivial pairs are possible. Those kind of numbers are called composite numbers. This way, we can classify all positive integers into 3 categories: prime, composite, or 1. 1 is 1. It's neither a prime nor a composite. It's a multiplicative identity or the unity, so it serves a little bit different purpose. Okay, so much for prime numbers. The next topic, prime factorization. I know you have been going through prime factorization problems since elementary school days, but finally, here's a proof that the prime factorization is always possible. Every integer greater than 1 can be written as a product of primes, like this. Here, each pi is a distinct prime, and then the power must be greater than 0, so 1 or higher. By the way, we're doing number theory, so everything here is integers, so greater than 0 and greater than or equal to 1, these mean the same thing. Remember that. So greater than 1 versus greater than or equal to 2, they mean the same thing. Let's go back to where they were. How about the proof? I hope everybody remembers the proof because I'm really certain that you already went through this in the Introduction to Proof course or Discrete Math course. Because this is a very, very typical example of strong induction. As a matter of fact, I cannot think of any other good example of strong induction at this level. I mean, there are many strong induction problems, of course, but they can get out of control difficult very quickly. And this is one of the really rare example that student can do and understand at that level. So I always cover it. If you remember, great. Even if you don't remember, pay attention. And prepare yourself so that you can reproduce this kind of proof from the scratch. Okay, here we go. We're going to use a strong induction, and the base case is n equals to 2. Remember, n is greater than 1, so not starting from 1, the next integer is 2, and in that case, there's nothing to prove. 2 is already a prime, so by itself, it's a prime factorization. A product of just one prime, but still, it's a product of primes. Next, inductive hypothesis. Assume for all positive integers less than n. To be a little bit more precise, integers greater than 1 and less than n, that will be a little bit more precise formation here. All integers greater than 1 and less than n, let's assume that. Previously, I thought greater than 1 is already here, so it was a bit too redundant, so I didn't emphasize that, but I guess it's a little bit better this way. So, true for all integers that are greater than 1 and less than n. Not just n minus 1, remember that. For standard induction, we just assume for the one previous. Just assume for n minus 1 and prove for n. Or assume for n and prove for n plus 1. That's what we used to do for standard induction. Strong induction requires everything less than n from the starting point. So in this case, greater than 1 and less than n. Okay, now let's prove for n. If n is already a prime, then there's nothing to prove. Just like this, it's a prime factorization just by itself, a product of just one prime. See? If n is prime, then there's nothing to prove. Now let's suppose n is not a prime. If it's a composite, then it can be decomposed to a product of non-trivial factors. Not just n times 1, but something smaller than n and something greater than 1. That's what I should have said. So non-trivial factors, non-trivial pair of factors, a and b, where a and b are both greater than 1 and less than n, so that n is a times b. Because it's composite, now pay attention to this. A and b are both greater than 1 and less than n. That fits the inductive hypothesis. So both a and b can be written as products of primes, like this. A can be written as p1 to the a1 power, p2 to the a2 power, and so on. B can be written as q1 to the b1 power, q2 to the b2 power, and so on. And then there may be some duplicate primes, so we can combine those and simplify. Whatever. In any case, we successfully wrote n as a product of primes. And is that wanted to prove all along? Yes, indeed. We wanted to prove that for arbitrary n, so that we set up the inductive hypothesis and we got it done. Okay, so much for the proof. Now, before moving on, let me make one more comment here. We just proved the existence of the prime factorization. We just proved that prime factorization is always possible for any integer greater than 1. Now here's another question. Is this expression unique? Or are there multiple ways to have prime factorization with different primes and powers? The answer is no. Expression is unique. We can prove that, and that proof is called, or that result is called, the fundamental theorem of arithmetic. Of course, it's harder, much harder. Some people call it the unique factorization theorem because the key point here is the uniqueness. But I'd prefer to call it the fundamental theorem of arithmetic or the fundamental theorem of number theory, putting these two together, both existence and uniqueness together. Of course, we cannot prove it yet. We have to take some steps. Let's take the first step. Let's prove first there are infinitely many primes. We use the proof by contradiction. Suppose that there are only finitely many primes, p1 through pk, and we are going to drive to a certain contradiction here. How to get that? Multiply them all and call it capital Q. And let's consider q plus 1. And q plus 1 is not divisible by any of those primes, p1, p2, p3, and so on, because of this modulo operation. Q plus 1 is this product plus 1, but this product is 0 modulo pi because pi belongs to this multiplication. So this part is divisible by pi, so that's 0 modulo pi, and the plus 1, so the remainder is 1 for this thing. So this q plus 1 is not divisible by any primes, and we just assume that these are all the primes there, so q plus 1 has no prime factorization. That contradicts what we just proved in 1.2. Every integer greater than 1 has prime factorization. Q plus 1, product of primes, that's non-zero, and plus 1, so that's greater than 1, but no prime factorization. That's a contradiction, and that came about because of this wrong assumption. If there are finitely many primes, then we have contradiction. There gotta be infinitely many primes. If there were infinitely many primes, multiply all them all, then we are going to get an infinity. So this kind of computation becomes meaningless. That proved there are infinitely many primes. And one more step before going over to fundamental theorem. Euclid lemma. Two integers a and b are said to be relatively prime if their greatest common divisor is 1. Remember that, and this result is known as Euclid's lemma. If a and b are relatively prime, and a divides bc, then a must divide c. The idea is this: relatively prime, so a and b do not share any prime factors. All the prime factors belong to c, so entire a divides c. But of course, you cannot use that kind of proof here because we'll have to use Euclid's lemma to prove the fundamental theorem. So you cannot use fundamental theorem and the prime factorization to prove Euclid's lemma. We have a circulation of logic. We have to do something else, and I hope you guys remember that something else is Bezout's linear combination expression. Express 1 as ax plus by and multiply c to both left-hand side and right-hand side, and then manipulate so that factor a out and a divides c. So in the end, we have Euclid lemma. The special case, if a is a prime number, then it is relative prime to everything except for the case that p divides that number. So we have this conclusion instead. So relatively prime means this is false, or if you go with a, then this is false. And then we can inductively extend this idea into arbitrary finite product. Instead of just a times b, consider a1 times a2 times a3 times and so on. If p divides that product, then p must divide some ai. You know, p is a prime, so it cannot be decomposed into smaller factors. Part of it goes to a1, some part of it goes to a4. That kind of things cannot happen. But of course, that idea, that argument is imperfect because I'm using prime factorization idea to prove eventually prime factorization in fundamental theorems. So I cannot do that. I have to go through a little bit harder way through Euclid lemma and Bezout's linear combination expression and things like that. As for the proof, they're all here. So I'll just leave those to you. This one too. All right. Finally, one more. In a special case where all these a1, a2, a3, they are all primes. In that case, p dividing by ai means p is equal to some ai. Why is that? If a prime number divides another prime number, but the latter prime number has only two factors, 1 or itself. The prime number that we begin with is not 1, so it has to be itself. You see, p divides a1, ai has only two factors, 1 or itself. P is not 1, so it has to be itself, ai. And this way, if you have product of primes and prime divides that product, then p belongs to one of those. And this final expression there is going to be useful proving the unique factorization theorem or the fundamental theorem of arithmetic, which we are going to start shortly.